Welcome to this section. Previously, we've trained our model and we've obtained some results. Now, once we have the results or once we get the outputs, it's time for us to convert it back to the initial referential we had, which is that of the image itself. Now, supposing we have this kind of output where we have x center 0.2. So supposing we have this output and we have 0.2, y center 0.3, width 0.6, and then height 0.4. Now, this isn't exactly what we need to be able to come out with this bounding box. But if we transform this using the same techniques we had used initially to transform our data from this bounding box into this kind of values, then we shall be able to obtain this bounding box. So supposing we have these values, which we could understand clearly from here, as we see the x, we go from this origin, x 0.2, y 0.3, then the width is with respect to the whole width of the image. So this is around 0.6 of this image, and then height is about 40% of the full height of the image. So that's how we obtained this, and we did that already. Now for the next, let's suppose we are trying to get these values now in this referential of the grid, where we have a 7x7 grid. Now what goes on here is we have 1, 2, 3 plus this 0.2. So it tells us that with respect to the grid, this is the x coordinate of the center is at value 3.2, and with respect to y direction, our y center is value 1, 2, 3.3. So we have 3 positions, and then in this we have 3.3. So once we get that, we now convert, or we now leave from the grid coordinate system to the image coordinate system. To do that, we'll do the same transformation we had done previously, where we divide by the current grid system or the current coordinate system and multiply by the coordinate system we want to get to. So right here we have 3 plus 0.2, that's 3.2 divided by 7 by 500. Then we have 3 plus 0.3, 3.3 divided by 7 times 281, considering that the height is 281. Now for the width, we have 0.6 times 500, because to obtain the width we had divided the value we had by 500. So now to get it back, we need to multiply by 500. The height same, multiply by 281. Now finally we've gotten this, so we could obtain the x mean and then y mean, x max and y max. So once we have the center, width and height, if we have the center, we subtract half of the width. So this is half of the width, so we'll subtract half of the width, so we can go these steps and then arrive at this position. So that's how we get x mean, and then y mean. Y mean, we also subtract half of the height. Then for x max, we add half of the width to the center, and then for y max, we add half of the height to the center. So that's how we obtain x mean, y mean, x max, and y max. Let's now get into the code and test our model on this test image. Now note that this model was trained on very few images, so actually this is part of the training data. So we expect our model to do its predictions perfectly. Now we start with the test image. We have the input dimension, which we've defined already, so we'll take this off. We have the image load with the target size. We collect the image width and the image height. We have this other image which we shall use in OpenCV to actually show graphically the results of the output. So this image is what's going to be passed into our model, this variable image, whereas this is going to be passed into OpenCV, so we could see graphically what our predictions look like. Then we now predict. So we have our output, which is gotten from model or predict of this image. Now we have this expand names because our model has a batch dimension. Now we have this threshold of 5, which we shall understand shortly why we need it. For the next, we have the value for the confidence score. So we could have this confidence score. This other one is then the next, after getting this output, we'll try to collect or gather all the different positions where the confidence score is greater than the threshold. Now the reason why our threshold is a 5 instead of a value like say 0.5 or 0.6 or any value between 0.5 and 1 is simply because, if you could remember from the loss we had defined right here, the way we defined the loss was such that after we get our output, we pass it through a sigmoid function. So the way our model learns is that it doesn't output a 1 when the confidence score or when it sees an object. It instead outputs a value such that the sigmoid, or let's define the sigmoid, such that the sigmoid of that value is going to be greater than or equals to a value like say 0.8. So if we have this, if we return 1 divided by this, we have sigmoid of, let's take a value like say 2. So if we have this, so if this is actually our threshold, then it means the threshold we have to define up there has to be value 2. Now if we wanted our value to be greater than say 0.99 before we consider it to be or consider that we have an object in that box, then we should have at least a sigmoid of 5. So that's what we constrain. That's our threshold. Our threshold actually is 0.993. So that's why our threshold is considered to be 5. Now once we've selected these outputs, we could print this out, selected output. So you could see clearly from here our selected output, which is basically these two positions. Then after the selected output, we now have the objects. Now the objects here actually happens to be part of this, where we have the classes. So note that the first 22 values are the classes, the next 4 are the positions, and the last is the confidence score. So this is the last, and now this is for the classes. So yeah, we could also print out this class. So if we have here objects, you see we have 15 and 15. This tells us that this belongs actually to the same class, to the object of class 15, and this happens to be a person. So this tells us that in this we have 2 persons already. So basically from this we can create an object, or more specifically a person counting application, where from this we now know that there are 2 people in this image. Now for the next part of this, we define the final boxes. We define because actually we are going to be extracting the objects. We extract the boxes because we need the boxes actually to be able to plot that, to draw it on an image. We need the object to say that for each box, this box belongs to this object, and then that's fine. So we have that. Then for this, now we could go ahead to extract these boxes. So right here we have this for loop. Could uncomment this. So we are going in for each and every bounding box. Now the bounding boxes, and then we go through all the object positions, or positions where we find an object. So these object positions happen to be where we have this. So we could take this off from here. Let's say object positions equals that, and then let's take this off from here. So we have the object positions. So yeah, we're gathering all the object positions. Now once we have this, we can now go through this. So we go in through each and every position. Actually this should be position. Now we have that, we get a position. Let's change this to position, pose. So we have the position, we get the output box. To get the output box, we basically have the position 0, position 1, position 2, and then we extract the box. So let's do this. This is position. We could actually print out this position. So let's do print of position, comment section, and we have that. So this tells us that our object is found at the position or batch size. Obviously this is a batch dimension here. So we have this position 3.2 and position 3.4. So that's where our object is found. That's around the center. That's where our objects are found. Now once we have that, let's uncomment this. That's fine. As we've seen here, we've gotten this output position 1, position 2. So just like saying output of 0, 3, 2 or output of 0, 3, 4. Then we collect the boxes. We could also print out the boxes right here. Output box. So there we go. Yeah, our boxes we get. Now once we have these boxes, we have to repeat the transformation we had on the slides. So if you look at this carefully, we have the x-center calculation where we get this in the coordinate system of the grid or the grid coordinate system, the same formula we apply. And here we find the width and the height. And then finally we get the x mean, y mean, x max, y max. Now note that if you have an x mean less than 0, set it to 0, y mean less than 0, set it to 0, x max greater than the image width, we set it to the image width, and then y max greater than the image width, we set it to the image height, or rather yeah, image height. Then finally we have this final box, which now takes this, where we also have the objects. Recall we had the objects, the actual object here, where we took this tf.max to be able to have this value where we had 15 here. So we'll get the where we have the maximum, where our the class in which our object belongs. So what happens here is we have now a final box which contains the bounding box and the object in question. So let's take this off, and that's fine. So with this we could run this now. Let's run this and have now the final boxes. So we could print out the final boxes. So there we go, we have this and we have that. So this tells us exactly where they're positioned and what they are actually. Now the next step actually is that of non-max suppression. Now in this particular example we may not face that problem, but that's a very common problem which we shall now look at. Many times when doing predictions, we may end up with bounding boxes which are surrounding a given object and all predicting that same object. So supposing we have this person, for example, or let's take this one here. We have this bounding box which surrounds this object. We have this other bounding box still surround the same object, and we want only one bounding box to surround the object, obviously, because we just have one object right here instead of two. So no need for these two bounding boxes. It's the same case right here. We have three bounding boxes surrounding just one object. The way we solve this problem is by using the non-max suppression algorithm. With the non-max suppression algorithm, what we do is we look at those boxes with the highest confidence scores, and then we look around those boxes. If there is any box which has an IOU greater than a certain threshold, like supposing we have a threshold of say 0.3, now we could see clearly from here that the IOU between these two boxes, this box with the confidence score of 0.7 and this one with the confidence score of 0.9, is actually greater than 0.3. So in this case, what happens is that we look at this box with a higher confidence score. Obviously from this examples is the second highest confidence score, because we go in a decreasing order of confidence score. We start with this, we go to this next, and then once we get to this, we look around it, which box has an IOU greater than, supposing 0.3, it could be 0.5, it could be 0.9, depending on how much we want to apply the non-max suppression. So if we're supposing that threshold is 0.3, now what happens here is the non-max suppression algorithm is going to suppress this other box right here because it's very close or resembles this box a lot. And so that's how we get to take this other box off, and we're left with just one box. Now if we look at this one right here, if we look at this other predictions where we have these three predictions. Now supposing we want we have an IOU threshold of 0.3. Once we come here, we start with this box because he has the highest confidence score. Then we look around it. If we take, for example, this box, we could, so let's suppose that the IOU between this and this isn't up to 0.3. It means this box is not going to be suppressed. Now if we look at this other box, if we suppose that the IOU is greater than 0.3, then this box is going to be suppressed. So at the end of the day, what we get now is this new predictions where we have just this one box surrounding this object and these two boxes surrounding this object. Now note that one of the aims of coming up with efficient object detection systems is so that we should even avoid the case where we need to do the non-max suppression. But in cases where it happens, we can simply apply the non-max suppression as we've just seen. Now coming back to the code, let's uncomment this region. What goes on here is we have the final boxes, the final scores, because the scores will help us in knowing which boxes to start with first. And then we have the object classes, which we've extracted from the final boxes. We have the final boxes themselves, that's the X, Y, W, H. And then we have the non-max suppression, which is part of tf.image package of TensorFlow. So with this non-max suppression, what we're going to put in is the final boxes, that is each of the boxes. We're also going to put in the final scores so that we know that for each box we have its particular score. And then we have the maximum output size, which was set to 20. We have the IOU threshold, the threshold we've been talking all through about. Now if we have a threshold of, we could have a threshold of 0. Or threshold values ranging from 0 to 1. So let's take for now 0.5. So that's the threshold we talked about in the slides actually. Now right here we have the score threshold, we'll set it to -infinity. So with this we could now run this and have the NMS output. Obviously in this particular case, this, as you could see, these two persons don't actually are not very close to each other, so we will have the NMS output showing us that we have this box which has been selected and this other box selected. So as you could see right here we have 1 0. It tells us simply that this one has a higher confidence score as compared to this. So the NMS, or the non-max suppression, started with this. It then looked whether this was very close to this. It wasn't, so we started with 1 and then went to this 0 box. So box 1 and box 0 are valid and can go through. So once that's okay, we can now have our boxes. So right here we could print out the final NMS boxes. As you can see from here, it's basically this box and this other box right here. We have this box and that box. In the next step, we are going to be using the OpenCV library to print out the rectangles and the text, that is the actual object located right there. We shall just uncomment this and run it so you could see the output we're expecting to get. So this is exactly what we expect to get. We expect to have this bounding box, as you could see right here, with the person, or that with the object class, and then we expect to get this other one with the object class. Here is actually person, so that's it. Now we could uncomment, we could have that. Okay, so let's say we're going now for each of the boxes. So we're going to print out, or we are going to draw out on each of these boxes a rectangle, or each of the objects a rectangle, and then we're also going to put text. So we're basically using OpenCV library, as we've said previously. We have CV2, the rectangle. We're taking the image, which we've defined already. We have the box, that's the boxes, or basically from this we have box 0, box 1, box this, and box that. It actually works with the x min, y min, x max, y max. So that's why we have this, as you can see clearly from here. Now notice that these are actually tuples. So we have the x min, y min, and then here we have the x max, y max tuple. And then we have the box's color and then the thickness of the box. So if we modify this to say 20, run it, you see it becomes, the box now becomes very thick. We send them back to 1 and then run it again. See, everything's fine now. Then we move straight to the text. So for each of the objects, we have the object class. Recall we had the object classes which we had gotten from here. So we have the object classes, and then we have the corresponding positions. Now the way we want to do this is we actually want these classes to be just above or on top of the boxes. So that's why we locate them as its position. So we're locating the x min, y min, and then we also have the color, we have the thickness, we have the font, and that's fine. So once we have this, we do this for each and every one of the boxes. We show the image, and then in case we press on a key, we could actually stop the image, and then we destroy all windows. So that's how we obtain these results.